Hello class. So this is the makeup class for last week, which we missed. So this should be last week, Friday. I don't remember the date. When I remember, I will write. So we were doing number theory, and where we left off was like seeing GCD of two numbers in a manner, and that's where we will start off our class from today. That we'll start with a theorem, as I have mentioned in my previous lectures. It's called Bezout's theorem. So what does Bezout's theorem actually say? Bezout's theorem says let a be two integers, not both zero. So a and b both can't be zero. Then there exists integers x and y such that GCD of a comma b equals ax plus by. This is known as Bezout's theorem. Okay. Now let me point something out in case of Bezout's theorem. We are seeing something of this form ax plus by equals something where a, b, c, x, y, all of them are integers and not all of them are zero. Not a and b are not zero. Okay. So these sort of equations with these conditions is called a Diophantine equation. Of order 1, because it can be like ax square, bx square, something like that. Okay, but since it's just basic thing, just need the linear thing, we can deal with it only. So it will become then order 2, order 3, and so on, so on. These sort of equations are called Diophantine equations. Okay, so that equation we are dealing with here is a Diophantine equation, but that is not the case. The case we can say is what Bezout's theorem essentially means is we can write the greatest common divisor of A and B as the linear combination. Linear combination means in this form: A into some integer plus B into some integer. Okay, linear combination of A and B, which is actually a huge thing because you will understand it later what actually it signifies. Okay. Now, before we go to Bezout's theorem's proof, actual proof, let's take a moment to think about how did we do the proofs in case of um, say the division algorithm, or mostly the division algorithm. And the division algorithm is a very strong theorem. Okay. And what we use for the division algorithm and what we will be using for these foundational theorems throughout number theory is the principle called well ordering principle. I will repeat the well ordering principle once again. The well ordering principle states that the well ordering principle states that if a set S is a non-empty subset of the set of natural numbers, if we write as n, I'm receiving it well. Yeah, sorry for the interruption. I had to take that call. Yes. Then S has a minimal element. Okay, so that was the well ordering principle that we have done in class earlier. Okay, now let's get back to the proof. Let us consider the following set. Okay, let's not make it x and y because we already have an x and y. Let's call it AU plus BV, where U and V are integers, and also let me add another criterion. And AU plus BV is positive. So this information makes thus T is a subset of a set of natural numbers. T is non-empty, since A belongs to T, or you can argue that B belongs to T if U equals U is not 0. U equals 1 and V equals 0. Then you can have this T is non-empty and T is a subset of the set of natural numbers. This means, this implies well ordering principle that T has a minimal element. Right. Now, let us think about that. If T has a minimal element, then what does it actually mean? Let's give it some time to sink. Why is it non-empty and stuff? We have done it previously in the division algorithm. Why the set is non-empty? It's very similar to that. Okay, let's get back to the problem. Now, since T has a minimal element, let us call that minimal element as, let's denote minimal element as D, where of course D is positive because D is an element of the set T, right? And D is the smallest possible element of the set T. So D must be positive because T only contains positive integers by definition. Now, we already know that since D is an element of T and T contains elements of the form AU plus BV, where U and V are arbitrary integers, then for some X and Y, there we can we can say that and say D equals AX plus BY for some integer X and Y. Why can we say that? Let me repeat it again. since D is an element of E, that means D must be of the form AU plus BV for some value of U and V. U and V are arbitrary integers, right? So whatever element of the set element that set T has, all of them looks like AU plus BV, where U and V can be any integer. Now, if the value is D, this value is obtained for some specific value of U and V, right? So then that case we take U to be X and V to be Y. From there we get this thing. Now did you understand what happened there? Okay. So now we have achieved one thing, that we have shown that D equals AX plus BY for some X and Y integer, right? We have shown that, but we are lacking something. Next part we need to show is D equals GCD of A and B, because Bezout's theorem wants us to show that if GCD of if A and B are integers, not both of them 0, then there exist integers x and y such that GCD of A and A comma B equals AX plus BY. So we need to show that D is the GCD of AX and BY. And also mind that it's a very important thing to understand that since D is the smallest element, the minimal element of T, then the GCD is the minimal element of this set. We will discuss that in a later corollary. Do not worry. We'll discuss that. Take some time to scan it. Okay. Now, since you have a good, well grasped the basics, let us get back to proof we have in hand right now. So, since D is the GCD of A and B, then it implies think about this. We have considered D to be the GCD. How does that actually help us? How does that actually help us? Because we want to show that D is the GCD. When can we say that a number is the GCD? Under which conditions can we say that a number is the GCD? It has to be two conditions, right? Condition number one, that D equals D is the greatest possible yes, D divides A and D divides B, D divides both. Also, if C divides A and C divides B, then D is greater than or equal to C. That for any So what does it mean? That D is the greatest of all common divisors of A and B, and D is a common divisor of A and B. Two conditions for it to become the GCD, right? Now, suppose D does not divide it. We will be approaching it by the principle of mathematics, the contradiction, proof by contradiction approach. Then, by the division algorithm, there exists unique integers Q and R such that A equals dq plus R with the criterion R is greater than or equal to 0 and less than mod A actually. I don't need to consider it to be positive always. It can be negative as well. Okay. Now the second part comes here. So if A equals dq plus R, it implies R equals A minus dq, right? Give it a little time to sink in. Okay, fine with it. So we can write this as, write it one after the other if you want to. So A minus, what is D? D was AX plus BY. We already proved it, right? That D equals AX plus BY. We just need to show that D is the GCD. So A minus AQX plus BQY. So it's A minus AQX, sorry, minus BQY, which we can write as A into 1 minus QX plus B into minus QY. Now, since Q, X, B, Y, all three of them are integers, we can say that one minus QX, comma, minus QY. This is also, these two are also integers, right? So if these two are integers, then we face a big problem. If these two are integers, then we face a big problem. And what is this problem I'm talking about? The problem I'm talking about is, then we can write R equals A into some integer u naught plus B into some integer v naught, where u naught is 1 minus qx and v naught is minus qy. A into, and since R was positive, that will imply this number is also positive, right? Because R is the remainder. Remainder is always positive. So A into V naught plus A into U naught plus B into V naught, this number is also positive. This means A U naught plus B V naught is an element of T, which is the set which looks like A U plus B V, such that it's a positive integer for each and every U V integer. Right? So A U naught into B V naught. Remember, V naught and U naught, they are not arbitrary integers. They are fixed integers because Q is fixed, X is fixed, Q is fixed, Y is fixed. So V naught and U naught and V naught are fixed integers. Okay. So it's an element of T. Also note that R is greater than 0, and I think I have made a mistake up above. I wrote somewhere that R should be within mod A. Yeah, I wrote that R should be within mod A. I need to modify that. It should be mod D, because not no necessarily mod D because D is positive, because here the divisor is D, not A, right? It should be less than the divisor. But we also have this thing that R is positive, that means, and R is less than D. These two facts together imply that R belongs to T and R is less than D. And also remember this thing, D is the minimal element of T. So it's a big red flag because it will imply that R is the minimal element of T. Right? Which directly opposes its views. Understood? So our base assumption that D was the minimal element of P, if this is true, then R must be equal to 0. If this needs to be true, then R must be equal to 0. Right? Because our assumption then, as it implies, our assumption that D does not divide A is false. Understood? Now, in a similar way, one can show that D also divides B. Very same way. You use contradiction and then show that. And D does not, you assume this D does not divide A, and then you show that D actually divides A. Assume D does not divide, sorry, B, and just like last, show that it gives a contradiction. Understood? So now we have actually uh, defeated two impediments in our path. What are the impediments? The first impediment is that we have shown that b is equals ax plus by for some x and y. Now we have shown that d is the common divisor of x and y, a and b. But we also need to show something more. What is that? What we need to show a little bit, we need to show this thing, that now we need to show that d is the greatest of all common divisors. Okay, so how will we show that? Assume C is a common divisor, is an arbitrary, random, some any common divisor of A and B. Okay, then what does it imply? It implies C divides A and C divides B. So if C divides A, then C divides AX for our X, and if C divides B, then it implies C divides BY. These two together imply that C divides AX plus BY, because C divides both AX and BY. So C divides AX plus BY, which implies C divides D, because D was AX plus BY. Now, if a number divides another number, what does it mean? The divisor must be less than the value of the dividend, right? So C is a common divisor and C is less than D, less than equal to D. For any C, for any common divisor C, it is true. Sorry. For any common divisor C. So what does it mean? That means D is the greatest among all the common divisors of A and B, which is specifically the GCD of A and B. Understood? This is how we prove our first theorem. Okay, good. Now let's give you some time to let it sink in. Uh, Hello, am I audible? Let's continue again where we left off. So we have proved the Bezout's theorem. Now we have certain corollaries regarding Bezout's theorem. Let A be as above, then the set defined in the theorem T, that is A u plus B v positive, such that u v are integers, is explicitly the set of multiples of D, which is as defined as the GCD of A and B. Okay, so what is this set explicitly as we were talking about it? This set is, you can write actually T as T is D of K, where K is any positive integer. K is an integer, K is a positive integer. So T is explicitly the set D, 2D, 3D, and so on. It has a huge implication in higher mathematics. When you will read higher mathematics and in the group theory, you will see something very interesting about this. Why Bezout's theorem is so important and what the corollary actually means. Okay, but let's not ponder over it right now. We have far more easier and not relatively um, intuitive things to work on. Okay, so now is the part of our proof. So P was the set AU plus BB such that which is positive, such that UV are integers. Okay, no doubt about that. That was the set that we defined in our question explicitly. Now, why are we saying that um, it's explicitly the multiple of the multiple of the key contains explicitly the multiples of D, namely D, 2D, 3D, where D is a GCD. Okay. Now let us remember one thing. D was the GCD of A and B. That means D divides A and D divides B. Okay. So that means D divides AU for any integer U, and this means D divides dV for any integer V. Okay, so if you combine these two together, you will have D divides AU plus BV for any integer U and V. So it doesn't matter what integer I choose, it will always divide AU plus BV. Okay, clear? Next, let's come to this thing that it essentially means that whatever integer U and V we choose, D will always be a multiple. Dk equals AU plus BV for any U and V. Now note that this choice of K, the K is dependent on choice of U, comma V, V. Right. So what it essentially means is if A equals 1, I have certain x and y, we get certain x and y integers such that D equals ax plus by, which can be justified with the help of Bezout's theorem. Because we know there exists such x and y for which the GCD can be written as a linear combination of x and of A and B. Namely, there exists integer x and y for which D equals ax times b, by. Right? So whatever value of k I choose, I will have some different thing. Understood? So if it is 2D, then I can write it 2 into ax plus by. It will become a into 2x plus b into 2y. Similarly, for any natural number n, if I write nd, I can actually write it as n times ax plus by, which follows from Bezout's theorem, which accordingly I can write as a into nx plus b times ny. Since x is an integer and y is an integer, then nx and ny are also integers, right? So it means for any natural number u and v, sorry, n, a times nx plus b times ny. This is explicitly the elements of set T, right? And x, y are fixed integers. So what is that? What is a into nx? A into nx is n times b, where n is any arbitrary integer, which is exactly what I wanted to prove, that T is the set which explicitly contains all the multiples of the GCD of A and B. That was my target. Z plus and n are essentially same. Okay, Z plus is 1 to infinity and n is also 1 to infinity. Okay, clear everyone? Which completes our tree. Okay, next we have another theorem. Let A, B, C, two integers, not both 0, then sorry, such that they are relatively prime. Their GCD is 1. Yeah, not both of them 0. Then, and they are relatively co-prime. Then there is a less than y for which 1 equals ax plus by. It looks pretty similar to Bezout's theorem, where d equals 1. Okay, this is a theorem whose proof I will leave to you to understand and try to do it yourself. Proof. There are some things you need to do on your own. Okay, and there is also a corollary, which will also be a corollary means it is directly followed from the theorem. Okay, follows from the theorem. Let A be the integers, not both 0. Then GCD of A by B, comma B by B equals 1, where B equals GCD of A and B. Okay, this is also your homework. Now, I will like to say a few things about this last one. It's very intuitive to understand that what it is actually. Because see, GCD of A and B is D. So you can write A equals dk1 and B equals dk2, right? So you can actually say that A by D is k1 and B by D is k2. Now D is the only possible common divisor of A and B, which has the only common divisor of A and B which has the largest magnitude, right? So K1 and K2 can never be common divisors of A and B, right? So that means their GCD must be 1. It's pretty easy to understand. Okay, this is the physical implication, if you want to say, of this corollary. Okay, okay, good. Now we have another theorem. Theorem. Yes. Let A divide C and B divide C with the GCD of A and B with 1, B1. Okay. Of course, I don't need to say anything that ABC, all three are integers. Okay. Then AB divides C. So I will try to give you an example of this. So A divides C and B divides C. So um, 2 divides 12 and 3 divides 12. And the GCD of 2 and 3 is of course 1. Then it actually follows that 2 times 3 equals 6 divides 12. So you can have one example to understand what it means, what the theorem actually means. Okay. Now let us get back to proof of the theorem. So we know A divides C and B divides C. What does that mean? With GCD of A and B 1. So by Bezout's theorem, you can write there exists x comma y integer. Now remember, this x and y in Bezout's theorem, these are fixed integers. So their existence is dependent. So we will have some x and y. We will not have we will not have a set of values of x and y. For different values of x and y it will hold, maybe. But x and y is not necessarily unique. For only one x and y it will hold, not like that. But we will have some x and y. I forgot to mention that. Okay. Such that 1 equals ax plus by. Right. Now we also know a divides c, which implies c equals ak1, and b divides c. C equals bk2. Can we draw something from here? Perhaps not. It's not the ideal way to do this. We can do something otherwise. We know that we can write c as c times 1, and we can write 1 from here, this equation. We can write that it is ax plus by, which means it is c into ax plus c into by. And now we can use our fact that a and b both divide c. A divides c means c equals ak1 or some k1 integer, and b divides c implies c equals bk2 or some k2 integer. Now let us modify this thing as follows. Cax, I can change c into, now I have ax over here, right? I finally need to show that AB divides C. So I need to take a AB common out from this whole thing, right? So I may need to replace BK2 in place of C times AX plus. Now I will substitute A here actually because I already have a B here. Next step, I can take the AB common out and I will have K2X plus K1Y. K2X into K plus K1Y is an integer, right? Which implies we divide C. Clear, everyone? Okay, that's it for today's class. Okay, I will publish another video that will be on it will be a 1 hour video explaining all the problems that was given in the exam, a doubt clearing class. So those two will be merged together to build one class of 2 hours. Okay. So good night, everyone. Watch the video. If you have any doubt, don't hesitate to WhatsApp me, call me. If you want to write in the comment, I will try to publish on YouTube and then send you the link so that you can do it. You can see the video as much times as you want. Okay, as many times as you want. That's it. We'll see you this Friday's class. I hope to see you in this Friday's class. I'm outside Kolkata. I came to Chennai for an important academic work. That's why I was not able to take your class last week. I had to travel Saturday morning, early morning. Okay, we'll see you. Hopefully, we will see you. We will meet this Friday. Good night. Best of luck.